There's actually one attack that if you have an RSA Chinese remainder theorem implementation, you can actually glitch it once and once do a normal execution, and just from the difference of those two you can recover the entire key, which is pretty strong, you could say. Now if you really want to kill your target, that's not too visible. There's actually somebody who tried to do fault injection using a microwave oven. That was more of a temporary, or more of a permanent glitch. Now this is the kind of thing that we use in the lab for glitching right now, both voltage and clock. It's an FPGA-based machine, which basically allows you very precise control over your glitching. So what we see here is if you, for instance, do a very quick clock glitch, you can skip instructions that way. If you do voltage glitches, you can see that if there's, for instance, a fetch from memory, that typically takes more power. If you put the supply voltage down right at that moment, you can actually read either 0 values or 1 values. So there's all kinds of cool things there. But we also use this same thing for triggering our laser setup, which is very cool. So optical fault injection was actually originally used to simulate X-rays in space. So X-rays are quite high energy radiation that triggers all kinds of faults in your chips. And some guys figured out that actually visible or near infrared wavelengths actually are much more effective in glitching chips. So what we do is we implement two types of attacks. One is a front-side attack, where you're looking actually at the chip and you're shooting with red lasers. Because the idea is that depending on the wavelength, you get more or less penetration through your chip. And when you're on the sort of the business side of the chip on the front end, you can shoot it with a red laser, and you can have very effective glitching. Whereas if you're on the back side, you're actually looking at the substrate, which you have to penetrate all the way to the gates, and there you need to cause a fault. So that's why we use infrared lasers for that. We need to access the silicon to actually get to this. So I've actually heard of some guys who are able to flash right through a card, like they don't even need to open it up. But with a flashlight, you can just sort of glitch all the way inside there. We try to have a bit more control, so we actually need to open it up. This is what the front side of a smart card looks like when you drill away the contact pads. And you're actually looking at the back side of the chip there. So you're looking at the substrate. So once we see this, we're going to use the infrared laser. We can also do chemical etching on the back side. And then we're actually going to see the front side of the chip, which shows us all the gates and everything. For that, we use fuming nitric acid, which is a fun thing to play around with. It eats away all the epoxies, but it leaves the chip intact. Well, I guess you only try this when you're wearing safety goggles. So that's actually one of the smart card dies that you can look at. This is a bit of a dirty one. You see a lot of epoxy spots still on there. We found out that when you really want to have it clean, you're actually going to kill your card typically. So we usually don't go all the way, we just leave it a bit open. What you also can see is some of the more secure chips that actually have an entire layer, an entire active shield covering the die. And so you will just see like a snaking pattern going all the way over the chip, which is trying to prevent you from doing this kind of stuff. Now there's a number of low-tech attacks out there. One is using the photo flashlight, what I mentioned. You can actually also use this when the chip is opened up and use an aluminum foil with a hole in it. And you can use this to flip individual memory cells. You can use one of these guys, laser pointer as well. Same idea, you have better control over where your light is going. One of the things, these are, well, this one is 5 milliwatts, I think, yeah. The one we use in the lab is 150 milliwatts, so you sometimes need a bit more power. The challenges here are you need to have some accurate triggering, accurate focusing, and the power level is sometimes something you need to adjust. So this is what we have in the lab currently. Like I said, we have a 150 milliwatt red laser. We have a 10 watt infrared laser, so that's one where you really don't want to stand too close when it's operating. We have this XY gauge for scanning the surface of the chip. And we coupled it to the device I showed you before just for this accurate triggering. This device is actually not on the picture right now. This is when we're still playing around with it. So you see a piece of paper here, and we're actually writing our names on like a micron scale by burning holes in it. I still need to make a module to imprint a bitmap or something on that scale. That would be kind of cool. So once it starts operating, it actually looks like this. So you see the chip die, and it's scanning over it, and each time it's sending in commands, it's shooting the laser, looking at the output, and trying to analyze what's going on there. So that's pretty cool. This is actually the same chip that you saw before. This is a little bit unrealistic. I made this because you can see it for visualization purposes. But normally the laser is on so short that the camera wouldn't be able to capture it. But sometimes longer glitches also work. So the challenges when you're doing this kind of voltage injection is mostly finding that sweet spot in time or location just to glitch the right transistor. Nowadays smart cards have a lot of sensors in them as well. So they actually will sense light, or they will sense all kinds of glitches and then kill themselves. Well, obviously you need to avoid those kind of spots. Now we are quite clever with actually detecting that we're being detected, because the card will show different behavior, so we just cut the power at that moment. But you need to be kind of fast in there, as you might guess. But before that, there's a few stacks of dead cards in our office. And you need to have accurate triggering. So you need, nowadays, they all cause kind of timing jitter, so you need to really look at the signals there. Now, countermeasures to all these kind of things, I won't go into it in depth, but all the DPA attacks were first published by Paul Kocher from CRI, and they have patents for all these kind of things. So if you need to implement one of these things, you have to ask their permission. Conclusions. Side channel analysis, voltage injections, they're actually quite diverse fields. You need to know something about computer science, electrical engineering, crypto, even statistics. But for me, that's the fun part. I like a challenge, and I like multidisciplinary fields. Implementing countermeasures correctly and consistently is very hard. We see that. All these things are known, but people make mistakes, and also designers do, and it's our job to find out that they did. And that side channel threats pose, side channel attacks present a serious threat to a wide range of devices, and it's becoming more, I wouldn't say common yet to do it on embedded systems, but it's getting there. Lots of times the logical attacks are not working anymore, so people start to fiddle around and try to do these kind of things. And there's only one really way to really figure out if your device is secure, and that's just to measure it. There's also more cool talks that sort of relate to this topic. I think after this, even in this room, Andreas will be talking about TEMPEST for the casual election hacker. So that's looking at the emanations. Tomorrow, Job de Haas, a colleague of mine, will talk about side channel and embedded. So that'll be exciting. And Sunday, Travis will talk about more or less direct probing of things. And here's, I'll post the slides on the wiki later so you can read these references.